So hello friends, welcome back. We were talking about turbulent premix flames and we were discussing various aspects of its various physical aspects of it. We discussed the regime diagrams and how by using simple scaling relationships we can identify different regimes of turbulent flames. In particular, the most important are the corrugated flamelets and the thin reaction zone or the thin reaction zone regimes or the reaction sheet regime as such, and most of the aerospace propulsion happens in between these two regimes. So there is some can happen in the distributed distributed reaction zone regime also. Anyways, now we were proceeding to develop basically the models that can describe the propagation of the turbulent flame. And as you see that from the beginning video that we saw, if you just go back, this video that we saw that we could understand, it appears we can understand turbulence flame interaction by basically considering what happens on different isosurfaces inside the flame, isosurface of temperature inside the flame. Then the task would be to essentially describe the evolution of these isosurfaces under the impact of turbulence, okay, large scale turbulence to small scale turbulence. And for that we essentially went to describe you the G equation. We will just take a revisit at it, and basically this is a field equation. G equation is a field equation where you can describe a G field everywhere inside your domain, and then you basically select one of those isosurfaces of that G field. Say that isosurface is given by G x t is equal to 0, as you see here, okay, and that is that essentially these propagation and movement and stretching and folding of this isosurface mimics essentially the dynamics of a turbulent flame surface. And we said that if G is less than or equal to 0 as the reactants, G greater than 0 as the products, then the local flame, the local surface G must propagate with the local displacement flame speed, whereas the displacement flame speed is of course rate of the propagation rate of the surface with respect to the local fluid velocity, and this propagation happens along the local surface normal, which is normal to the surface, and then whereas this normal is given by this expression can be found out from the G field itself, which is given by minus of gradient of G divided by mod of grad G. And then this is the representation, the cartoon representing the G field, okay. So then we could derive this, and the final G equation was given like this, okay, dg dt partial dg partial dt plus u dot gradient u dot u vector dot divergence over the acting on the G field, and that is equal to sd times mod of grad G. Of course this is a nonlinear term because this can be essentially written as square root of grad G dot grad G, and that is where the nonlinearity comes from of this equation. Then there are specific methods. It cannot be directly solved by normal central differencing or normal finite differencing methods, and there are special methods available for doing this thing, for solving the G equation, that is not we will not discuss here. But then one needs to find an appropriate model for SD also, that is a local displacement flame speed. How will you find that? Because that goes into the input, that is an input into the G equation model, right, into the G equation. So that can be given as a function of the local stretch rate, the local tangential strain rate, which is AT, and local curvature, and this is an expression that we can use, whereas the curvature this curvature can be obtained from the geometry of the surface. Once again, this curvature essentially is the divergence of the normal vector. So once again, if you know the normal vector, which we have given as minus of grad G divided by mod of grad G, okay, so from that you can find this out, and AT comes from by projecting the local strain rate into the tangential direction, which also you can find out from the tangential direction you can find out from the local geometry of the flame surface, which is given by the field G. So this is how the local property, the local geometry of the surface and local flow properties are essentially captured into the propagation speed itself also. So whereas of course to the first order the propagation speed depends on the planar laminar flame speed, and then what we see here is that the local curvature and the local tangential strain rates can cause deviation from the planar laminar flame speed, but that needs to be accounted for in the model for the local propagation speed that goes into the G equation. Okay. Now, of course, another thing is that this is valid in the weak stretch limits, but yeah, we can use that with certain constraints as long as the stretching rate is not too high. So this works well in the corrugated flame-led regimes where the turbulence is not too strong, but people have done some extrapolations into the thin reaction zone regime also. Okay. So, of course, as you see that the SD models get involved in the thin reaction zone regime or the reaction sheet regime. Now, how do you use this for turbulence? Okay. Now, as you know, the biggest problem of turbulent combustion or turbulent or modeling turbulent flows is that your eta, that is the Kolmogorov length scale by the integral length scale, scales as Reynolds number to the power of minus 3 by 4, right. So, as the Reynolds number grows big, the eta L0 ratio becomes smaller and smaller, right. So, whereas the thing is that suppose you are solving an engine, okay, which is a domain which is the largest length scale is say 6 times L0, that is the integral length scale. So, but if the Reynolds number is very large, say of the order of 50,000, your eta will be extremely small, okay, very small, of the order of few microns. So, the problem is that then you need to grade basically from all the way from the 6 time of L0, which can be of the order of which can be of the order of say hundreds of centimeters to this to this length scale of few microns. So, your largest domain size has to be of the order of few say 100 centimeter, and your smallest length scale in your mesh, if you want to do by CFD, it has to, the grid size has to be of the order of few microns, right. So, that is the problem. I mean, that is why we cannot solve the what happens inside the engine using just by solving all the continuity, momentum, temperature, species equations as well as the constitutive relations as is, and that is why we need to seek models which describe their mean propagation, mean properties or their filter properties as is done in LES, large area simulation. Okay. So, that is the thing. Similarly, that is why we went to do the RANS RANS model, where you do not need so fine grades, because you are only interested in the evolution of the average quantities. Okay. So, whereas in the, as I said, in the LES you are only interested in the evolution of the filtered quantities. Now, those are not the instantaneous quantities. So, you lose some knowledge of the what happens instantaneously, but then we are more interested in the averaged statistical behavior of an engine rather than what exactly happens in the different instance. So, but the problem, as you have seen, that poses as a closure model, closure problem, whereas there are closure problems at different stages. For example, you have seen that there is a closure problem in the Reynolds stress terms, there is closure problem in the turbulent scalar flux terms, there is closure problem in the mean reaction rate terms. So, there are closure problem at different stages. So, same thing happens in a turbulent premise combustion also. So, if you have this, even if you have this exact equation for the propagation rate of the flame surface, which is governed by say G, even if we assume that this G equation can describe the propagation of the flame surface exactly, but then that is if you have a very good model for U and you can account in for density variation somehow in the flow field, but given that your G field, if you have a turbulent flame, this turbulent flame will be wrinkled at multitude of length scales, right. So, you basically need to, even if you solve this G equation, you need to solve for this largest length scale, which is again of the order of 6 times L0 approximately, right, because your integral length scale is 1/6 of the domain size, and your smallest scales will be also fluctuation will be once again of the order of eta or the flame thickness, whichever is smaller, something like that. So, your computational requirement still is very huge, right. So, what people try to do is that people try to solve for an averaged G field, that is you do not average exactly over the G field, that is not really done, but you just try to describe an let me just draw this once again. So, the idea is that suppose this is your domain and this is your statistically one dimensional turbulent flame speed, which is wrinkled at multitude of length scales, and you don't have the resource to solve such a huge mesh. And another thing of course is that even though this scale separation is eta by L0 grows to the power of Reynolds number to the power of 3 by 4. When it comes to mesh, it becomes it's always a 3D mesh in turbulence, because turbulence is essentially 3D. So the scale separation essentially gets not it grows to the power it grows in a cubic manner, okay, because your smallest scales has to be of the order of delta. So whereas your largest scales is of the order of your smallest scales is of the order of eta, and your largest scales is of the order of 6 times L0. So if you have to reduce your scale, your smallest scale by 10 times, okay, so your eta now is essentially your delta is essentially 1/10 of the previous delta. So what happens is that your actual grid size, or the number of grid points, increases by 10 to the power 3, not just by 10, because it's if you assume it is a cubic domain, okay, of the order of that, depending on the domain size or domain shape, of course, but it grows in a cubic manner. So that produces immense computational load, which is really not possible even. So the current gas turbine combustor, if you want to solve it by direct numerical simulation, where you will simulate all the way from the large scales to the small scales, that is simply not possible. So you need to use models. That is why we have industry essentially uses RANS models, and some there are also LES is also emerging as one of the possible models to basically simulate turbulent combustion in practical engines. Okay. So one of this model that was proposed by Karpov, Lipatnikov and Zimont about 20 years ago was this say the mean flame surface propagation. So this is not the average, but what it tries to say is that, say, I do not have the resolution to grid resolution to basically simulate all these small scales. So what I will do is that I will have a mean flame surface which can be considered to be essentially the average location of all these instantaneous flame surfaces. So on average, of course, you see that this flame surface will fluctuate around this mean. So this mean is essentially given by GM is equal to say this is another, of course, a different function, which is say given by G0, whereas this thing is equal to the instantaneous, which is given by G0, which is given by 0. So or this can be also given by G0, also given by 0 actually. Okay. So this is the propagation of this GM, which is supposedly the flame, the surface, which is averaged over all possible locations of the instantaneous flame surface. Okay. So this is the essentially the mean flame surface model, and of course now you have Favre is essentially propagating as a result of two things. It's now propagating due to the mean flow, okay, which is UI averaged, Favre averaged, and then it itself propagates with a, instead of the instantaneous and local displacement flame speed, this thing propagates with a mean propagation velocity, which will emerge to be essentially turbulent flame speed in the, as you will see later. So this is the this was what my domain was. This is the instantaneous flame surface, okay, and this is the mean flame surface, which has to be straight because it's statistically planar, and so it now behaves almost like a one statistically planar planar 1D flame, but of course its structure is very much different from the 1D flame because it is essentially averaged. For example, why it should be different is that we will see that there are two major points of difference. Number one, this thickness of the flame will be much thicker, thickness of this averaged flame will be much thicker than the instantaneous flame, and two, it will propagate much faster because as instantaneously as its surface area is much bigger than the planar laminar surface area, okay, it will essentially consume a lot more of the fuel air mixture than a planar laminar flame can consume, and as a result the resultant velocity or the resultant speed with which it will move is given by this turbulent flame speed, and it will be much greater than the planar laminar flame speed. Okay. So, this is the thing. So, now we need to understand basically this concept called ST. Now, if in a planar laminar flame or in laminar flames, the most important property is laminar flame speed. For a turbulent flame or a turbulent premix flame, the most important property is the turbulent flame speed. So, what is it and how does it behave? So, this is a very important topic of research that has been for the last several decades, and it is still kind of an unclosed problem, but we need to understand this because turbulent flame speed is what governs the propagation, stabilization or any such dynamic behavior of a turbulent premix flame. Okay. So, turbulent burning velocity, the research of turbulent burning velocity essentially originates from the works of Damkohler, who suggested two limiting cases, and one is the wrinkled flamelet regime and another is the another works in the thin reaction zone regime, which are the two regimes that we have seen. Okay. So, the turbulent flame essentially the turbulent propagation modes are fundamentally different in the two limiting cases. Okay. When the turbulent scales are larger than the flame thickness, that is in the corrugated flamelet regimes or the wrinkled flamelet regime, where there is no disturbance on the preheat zone structure by the turbulent eddies, then just turbulence increases the flame surface area by due to tangential straining without essentially distorting or disturbing the inner flame structure. But when turbulent scales are smaller than the flame thickness, then turbulent can modify the transmit processes also, because you see essentially turbulence has a very strong diffusive character. Okay. Whereas, but it is that diffusion arises essentially due to the convection and the essentially due to the convective terms and due to the Reynolds stress terms, which are essentially very much responsible for the diffusive nature of turbulence. Okay, because of the turbulent fluctuations. But you see that in a laminar flame essentially both the diffusive molecular diffusion processes as well as reaction are very important. If you remember, your flame speed was essentially the geometric mean of the reaction rate and the diffusivity, the thermal diffusivity, right. So, now if you have very strong turbulent diffusivity which essentially overrides your thermal diffusivity or molecular diffusivity, then this turbulent diffusivity can become an equally important or even more important parameter than the turbulent diffusivity, than the molecular diffusivity in this propagation rate or this global propagation behavior of the turbulent flames. So, in the preheat zone structure, if this is now the distorted preheat zone distorted flame shape, whereas in the thin reaction zone regime like this, let me just draw it. So, this is the preheat zone structure. So, where now you have eddies of different sizes distorting it, then these eddies will essentially can create turbulent diffusion inside the flame structure. Okay. So, that is one possibility. Of course, when you look into this in a statistical way, that is if you can now think that your flame you can essentially convert this entire different flame structures into essentially a statistical 1D structure, then also you will see that this turbulent diffusion will play a major role in essentially controlling the diffusive processes inside this preheat zone of this turbulent premix flame. So, when what we want to say is that when it is a corrugated flamelets regime, that the turbulence scales are much larger than the flame thickness, then turbulence only increases the flame surface area. Whereas, if the turbulence scales are far smaller than the flame thickness, that is in the thin reaction zone regime, the reaction regime, then turbulence can modify the transport process also. So, in this one we just only need to calculate the increased flame surface area, whereas in this one we might need to even calculate the enhanced diffusion processes that happens inside the turbulent flame structure. Okay. So, in the wrinkled flamelets regime, that AT, if we consider that the AT is the instantaneous flame area, whereas A is the projected area. Okay. That is what I mean is that let's say if you have a flame like this, Okay, so this is in 3 dimensions, of course. The flame will be 3Ds, and then this increased area. So now you just have an increased curve length over the planar laminar flame, which was a planar. So this is the laminar flame, which is say which had an area of say AL. Say it's a cuboid channel in which the flame is propagating. Okay, so then this wrinkled area has the surface area 80. Of course, a wrinkled surface area and a given in the same cross section will have much more area than the planar area. So this wrinkled area has a surface area of 80, whereas the planar laminar area AL or the projected area has an area A, or has an area A only. So then we can what we can do is that we can find out the relationship between ST and ASL, and as a function of AT and A. So what we can say is that, let us consider this is to be a cuboid in which this turbulent flame, as you see here, is stabilized. It is statistically stationary at this location. That means it is essentially fluctuating about this constant about this line A, okay, line or area A. So for this, as if you remember that for a laminar flame to be stabilized or stationary at a particular location, the reactants must enter into it at a velocity which is given by the planar laminar flame speed SL. So by the same argument, to keep this flame, this turbulent premix flame stationary at this particular point, the average velocity with which the reactants must enter into the flame is ST. Okay. That is in the other way, that if you allow this to be free, if you allow this to be a freely propagating flame, on average this flame will move to the reactants, will the average propagation rate of this flame into the reactants will be equal to ST. Okay. So ST is essentially a kind of a you will see that it is a average propagation rate of the turbulent flames of the turbulent flame. Okay. So now to compute that in terms of the area, what it will be is can be found out from here. That is if I say that, let us compare the mass fluxes. So the mass flux then, if this flame is stationary, then the rate at which the mass flow rate into the flame surface, okay, the mass flow rate into the flame surface is given by rho u times local SL. I consider the local flame speed to be essentially constant, times AT, whereas this is the flame surface area. Now this is the mass flow rate into the flame surface. Okay. And now if of course this is the mass flow rate that is going into the flame surface, and of course this is coming from the upstream mass flow rate, and if that has to be then the mass flow rate is being fed at a velocity at a speed which is equal to the turbulent flame speed, and this because the flame is essentially statistically stationary. So then we can equate this to rho u times ST times A. Okay. And so then my ST by SL essentially becomes AT by A. Okay. So this is the reason why our ST must be greater than SL, because your AT is much greater than A. Okay. So once again to clarify that so the rate this is essentially the rate at which this mass is being consumed. This m dot is the rate at which the mass is being consumed in this wrinkled over the entire wrinkled flame surface. Okay. And now of course the appropriate velocity locally with which this mass flow rate is going in is essentially SL, which is the relative velocity between the flame local flame motion with respect to the local fluid velocity, and that is why SL comes in. So, then we can equate it to an average speed with which the mass must be fed for the flame to be essentially stationary, and that is given by essentially ST. So, it is so we get that m dot is equal to rho u times SL times AT, and with which the mass is being fed into this thing, and then this we can equate that to essentially rho u times ST times A, and our then ST by whereas ST is the local is a global propagation rate of the flame surface, or if this is statistically stationary, it is the rate at which the mass this fuel reactants is of a speed at which this fuel reactant is approaching the flame surface, the overall flame surface, and then this is given by ST, and then ST by SL is essentially equal to AT by A. Okay. So, then since turbulence increases the area, AT is greater than A, which crosses ST greater than SL. Okay. Now, in the weak turbulence limit, it can be shown that that for this ST by SL is essentially square root over 1 plus u prime by SL square, but this is only true when u prime by SL is much less than 1. So, this is true only in a very weak turbulence limit, and this is not of very much practical importance, because we do not have situations in a practical engine which is weakly turbulence. We have situations in a standard engine which is strongly turbulent. Okay. Now, we go into a more formal discussion and methods by which the turbulent burning velocity of the turbulent flame speed ST can be obtained, because as you see that ST comes into the model for the G equation to describe the average propagation speed, average propagation of the propagation rate of the average of the mean surface, and it is used in different turbulent flame speed models for validation also. So, just like laminar flame speed is an important parameter for laminar flames, turbulent flame speed is also a very important parameter for turbulent burning velocity, but there are problems which we will see. The turbulent flame speed can be defined as the propagation rate of the mean flame surface with respect to the unburned gas and average rate of mixture conversion into products. So, that was our ST. Okay, this is what we described as ST, and it is essentially it is still kind of we still do not understand turbulent flame speed completely, and Peters describes in his book as that this is one of the most important unresolved problems in previous turbulent combustion, is determining the turbulent burning velocity. And if ST is turbulent flame speed, SL is planar laminar flame speed, U prime 0 is RMS of fluctuating velocity, integral length scale laminar flame thickness, then we want to seek a solution of ST by SL as a function of U prime SL L0 L. That is, if you have a turbulent flow which is completely defined by U RMS and integral length scale, and of course, other properties, the fluid properties are given, and you have a fuel air mixture by which you where your flame speed and flame thickness are known for the planar laminar flame, then can you, with these parameters, can you determine the turbulent flame speed as a function of the laminar flame speed. Okay. Now, there has been of course, people have tried to seek this, and there has been numerous experiments and there is numerous models and computations, but still this remains a little bit unresolved, and we need to do more research on this, and that is why I will give you some glimpse of what has been done. Okay. So, in the thin reaction zone regime, we have a very interesting idea from Damkuler. He said that for a planar laminar flame, the planar laminar flame can be written as, it is of course a unit of meter per second, and your of course a planar laminar flame has meters per second, and the diffusivity when Lewis number equal to 1 has an unit of meter per second square, and your time scale of the flame crossing time is essentially seconds. So, what we can do is that we can write this is a chemical time in terms of seconds. So, we can write this SL, of course, we know that we have written SL as essentially d times omega, whereas d is the diffusivity and omega is the reaction rate. Okay, and now we just want to write this omega in terms of a time scale. So, instead of a reaction rate, we just write a chemical time scale which is in units of second. So, then by scaling argument we can write SL is essentially equal to d by tau c, that is the thermal diffusivity by a chemical time. Okay. or we can write it as SL is equal to root over d times omega b also. Okay. Now, then what he says, then by analogy, in the turbulent, for the turbulent flame speed in the thin reaction zone, he is saying that Damkler is saying that your now your diffusivity is not just thermal diffusivity or which is governed by molecular processes anymore. Now, this diffusivity that you have here must be replaced with turbulent diffusivity. So, what if we just replace turbulent diffusivity in the similar way and keeping the chemical time scale to be same, or we can write this as essentially root over dt times omega b 0, that is the local reaction rate remains unchanged. So, then we can write St by Sl is essentially equal to square root of dt, which is the turbulent diffusivity by d. What is turbulent diffusivity? Turbulent diffusivity is, if you remember, that by the gradient transport assumption, your U prime C prime average, right, this prime C prime, this one is equal to minus dt times dc dx, that was what we wrote. Okay. So, this is whereas C was any species. So, this is the gradient transport assumption that we could write, and hence by that that is how the turbulent diffusivity essentially originates, and hence if you now we have to find out what is a suitable expression for dt. Now, since dt is given by has an unit of once again of meter per second square, we can write it in terms of the large scale turbulent parameters as u prime times L0. So, this is meters per second, this is meter. So, it is essentially meter square per second, essentially meter square per second, and we write of course d is equal to LL, which is the which is SL times LL, which is the local laminar flame speed times the flame thickness. So, then ST by SL we essentially get is u prime 0 by L0 divided by SL times LL. Okay. And this is nothing and as you know that if we say Schmidt number equal to 1, this SL times LL becomes essentially can be written as equal to D, which is equal to the kinematic viscosity. So, then this ST by SL becomes essentially so we can write SL times LL is equal to D is equal to nu. So, then ST by SL is becomes essentially equal to Reynolds essentially becomes equal to Reynolds number to the power of half. Okay. So, ST by SL should be equal to then Reynolds number to the power of half. So, this way we can have a scaling relationship for turbulent burning velocity. So, this is important thing. Okay. Now, why is this so important for gas turbine combustors? Because as we have seen that from this definition itself, the turbulent flame speed can be defined as the propagation rate of the mean flame surface with respect to the unburned gas or average rate of mixture conversion into products. Okay. This is one is essentially a displacement turbulent burning velocity, another is a consumption turbulent burning velocity, and so this turbulent burning velocity is a global in units of meters per second. It gives you an idea about what is the global consumption rate of the fresh mixtures. Okay, just like the planar laminar flame speed gives you an idea about how the mixture is being consumed across the flame in units of meters per second. So, turbulent flame speed gives you two things. It gives you an idea of how the mixture is being consumed, how fast, and B, and consequently it also tells you how fast turbulent flame speed can propagate, or reversely that to stabilize, to statistically make a flame stationary, what is the maximum velocity with which you can feed in fresh fuel air mixture. So, that essentially governs your combustor entry speed. Okay. In typical combustor, your entry speed is of the order of 40 meters per second. Okay. Of course, you have some aerodynamic means to stabilize, but this is far larger than 40-50 meters per second, even more. It can be 100 meters per second, but which is far higher than the laminar flame speed. Okay, which is of the order of say 30 centimeters per second, whereas you are stabilizing a flame as 100 meters per second. Of course, you do aerodynamic means, we create local low velocity regions, etc., but still this flame shouldn't have been able to stabilize if there was no turbulence. emissions. Okay. So, turbulent flame speed determines the total consumption of premix reactions and govern the mean location and global stabilization of the flame. So, in this engine, even in a TAPS combustor, which is a which is a flame like this, in a TAPS combustor, if you have to stabilize the flame, you have to know what is the turbulent flame speed, so as to design this engine properly. Okay. So, similarly, if you have to stabilize this lean premix flame in this low sol burner, one needs to know the turbulent flame speed, because this flame is being stabilized because the average velocity is equal to the turbulent flame speed of this flame. So, that is why it is important to know the turbulent flame speed, and next we will take up essentially the methods to analyze turbulent flame speed. Now, one can do some analytical derivation, and which we did, and we took up the G equation and took the spectral approach, and which will not go into details. And this expression of turbulent flame speed in terms of the G field comes from Kirsteiner, Schusten, Williams, where he takes essentially an infinite really long cuboid, and which is filled up with different of the surfaces. So, he shows that this ST0 by SL, which is the turbulent flame speed of a statistically planar flame, which is stabilized, which is stationary inside this statistically stationary inside this cuboid, and then he showed that then that is given by the volumetric average of the gradient of the mod of the gradient of the G field. Okay. So, and then using those, one can arrive at a expression which is similar to that of Damkohler, but not exactly same. One can introduce this stretch effects, and then ST by SL is given by 1 by Marsden number, which is the ratio of your Marsden length. If you remember that this is the Marsden length which comes. So, the Marsden number here is essentially your ratio of your Marsden length to the flame thickness. Okay. So, then this is given by for positive Marsden number of fuel air mixtures, then the ST by SL is given by 1 by Marsden number times U prime by URMS by planar laminar flame speed times integral length scale by the planar flame thickness whole to the power of half. Okay. And then we will show you some experiments in the next lecture to basically show that how one obtains these turbulent flame speeds using laboratory experiments, and how well does they fit into different kind of scaling laws, and how one can basically have good scaling laws for different kinds of turbulent flame speeds in different configurations, as well as for different fuel air mixtures over different ranges of pressure and URMS conditions. So, thank you.